So we talk about the introductions of particle physics. So in the standard models, there are some elementary particle, the quarks and the leptons with the three generation. There are two types of the quarks. One's the up type and the other one's down types. And the up types takes some of the two over three electric charge, and down type takes minus one of those electric charge. And each generation there are up charm subcoques and the down strange bottom coques, and the mass is ordering is up coques, down coques, strange charm coques, and the bottom and top coques. And in the leptons, the charge of the leptons written by the L with the minus one electric charge, electron, muon, and tau, and the corresponding neutrinos with the no electric charge, electron neutrino, muon neutrino, and tau neutrino. And each up type and down type and neutrino charge leptons can be swapped by the charged weak interactions. And these elementary particles that have a spin 1/2, but the other bosons, like some of the Bose carriers, but the interactions, the spin 1 or spin 0. First of all, for spin 1 gauge boson, there are four gauge boson. The proton for the U1 EM and the double plus minus charge for the charged interaction and the neutral interactions respectively on the gluon. Such as the electroweak parts that comes from the U1Y hypercharged and SCL lapandis gauge symmetry, and the QCD parts that comes from the S3 color symmetry. And in the spin zero parts, there's a Higgs boson double law, and the coupling between the Higgs and the fermion, all the bosons, then the such a particle can acquire zero mass. And the Lagrangian for the standard model can be written like that in the following form. The very simple form. The first of all, there are psi d psi, where the d is the covariant derivative here. So the d mu is written by the partial mu minus coupling I on the boson. So it gives the spin 1/2 and the spin 1 interaction, gauge interaction, and also it contains the kinetic term for the spin 1/2. And the second term is the Bill strength for the gauge boson. It gives the kinetic term for the spin 1. And the third term is also d mu is the covariant derivatives here. So it gives the kinetic term, the partial derivative kinetic term for the spin 0. And also a mu term, and there are Higgs spin 0. So a mu Higgs coupling is possible in here. So it can give the boson mass if the Higgs get the bar. And the fourth term is a core interaction. The Hubble, not Hubble's, the Higgs double laser and the left hand and the right hand fermions interactions. So spin 0 and spin 1/2 that are couples, and if the Higgs get the babs, then the fermions can acquire the mass. And the final terms is the Higgs potential. The quadratic term gives the spin juice the mass, and the quadratic terms give the setup interactions of the Higgs. And especially in the gauge interaction, there are three gauge symmetry in the standard model: S3, colors S2 Lapandes, and U1 hypercharge. But S3 case, it gives this only the color charged that participates in S3 interaction. That makes the hadron, which makes the gluon, or the which makes some of the baryons and the meson via the gluon. And the ST2, there are weak interaction. The old elementary particle, quick charge lepton and neutrinos are participate because all have such a weak isospin. And in the electromagnetic interactions, only the charges, quick and charge leptons are participate. Neutrinos are participate in the EM interaction. So the such interaction can be expressed as the Feynman diagram. This is a gauge interaction, two fermions and one gauge boson. The spin 0 and the spin 1, if the Higgs get the babs, and the such gauge boson gauge the mass and the interaction between the Higgs and the fermion, you call interaction, and Higgs get the bulbs and the fermion cause the mass. There are some of the we can introduce the dimensionless coupling constant alpha as is cancellable over pi. Where we use the natural units h by cos c equal to the 1. And the also coupling E can be written by the roots of the pi alpha. So the alpha is also called some of the structure constants or coupling constant, and they usually we use alpha instead of the E or GE. For the lactose magnetized case, the such a coupling constants is given by the 1 over the 137 very well known value. The Lorentz invariance amplitudes, such as S matrix, is a proportion to the alpha. There's the one E here and another one E here. So the probability of scares of the S matrix around scares are proportional to the scares, but it's such a tree level. In the wave interaction case, the coupling constant is one of the over the 30, which seems like the ladder and the electromagnetism, but the W boson and the G bosons has a mass, unlike the photon and the gluon. So there are some of the mass term in the denominators of the propagator of the W and the Z boson, and it is extremely larger than the momentum transfer. So the such a weak coupling constants with the WZ boson mass becomes a Fermi constant with the very small values. So the weak interactions has a very small interaction strength because of the large W boson mass is master in the denominator, and this is also similar to regime in the effective theory. And the case, the strong interaction, the coupling constant is almost 1, so the interaction is very large. First of all, in the electromagnetic interaction, the Fourier transforms of the S matrix becomes a Coulomb potential, so it's constant with the classical result. Also, we can obtain this result by using the Born approximation. And in the weak interaction case, is the relevant with the weather decay. If there is some of the coupling with the W boson, charge or wave current, then the types of the fermion particle changes between the up and the down. Up type character the 2 of the 3 and the down type the -1 of 3, so the electric charge are conjugate, and also the isospins are conjugate in these interactions, and also neutrino can be swept by the charge the lepton. In the QCD case, it can make the boundary state as hadron state. Some of the combinations of the QQQs, the baryon, and the QQ bar for the meson. And there are some of the learning coupling constants of the strong interactions that has asymptotic freedom behaviors for the large momentum. The coupling constants is extremely small, and in the long distance, it behaves like spring force. So the quarks are all the combined in the hadron state. There are some of the examples of the decays, like the neutron decay or muon decay. And those are some of the viewpoints of some introductions of the particle physics in the standard model. We saw that some of the elementary particle and there was some of the interaction and some of the coupling constant and the Feynman diagram. And now it starts with a very short experimental point of view, like the tactile or collide as measurement. So the point of this part is the particles are produced in the collider, some accelerated on the some of the natural source like a cosmic ray, and it can be detected by the several methods. First of all, the stable particles are proton, neutrinos, proton, which is not decay to the particle, and the long-lived particles like the neutron muons, which have a very long lifetimes because that is only relevant with the wave interaction. And also the pions that counts that has also very long lives particles of the hadrons, even is relevant with the strong interaction. because such a pion, the kaon is the lightest the particles in the hadrons. So first of all, such neutrons and the pions to decay to the other hadrons and the other quarks, and it makes some of the also neutrons decays the proton and some of the emits the decay. And by using the hadron calorimeter, which can measure the energy, we can talk such neutrons and pion. And the electric charge, the particle like the electrons, they can be detected by the several methods like the tracking or channel radiation when the particles velocity is faster than the refractive speeds of the light, and also radiation with as a brimstone can make the EM shower, so the electric charges are measured very easily. And the muon detectors by using the muon decay, and the photons can be detected by the EM calorimeters with also the energy measurement. And neutrinos opens the missing energy. It's hard to detect. It requires the very large volumes of the detectors. And in the LHC, like the colliders and detectors, neutrinos opens the missing energy. So the such a missing momentum is minus of the summations of the other visible particles momentums, and also we can confirm that the such a supersymmetric particle or dark matter, which is hypothetical particles as undetected particles which carries the missing momentum. Also, the neutrino can be detected by the liquid scintillator by using the inverse beta decay. It makes the neutrons at the excited state and the photons are emitted in the liquid scintillator. And there are several particle productions is possible in the collider, first of all the LEP in the cell, which collide electrons and positrons in the energy centers of the mass energy is 100 GeV. And the Tabatron, P and the proton and antiproton collider in the Fermi lab. And the LHC in the Saran is still learned in now, and the proton and the proton colliders up to the 10 TeV, and a very large luminosities in this die. The luminosity means that the repeatance of the experiment. So the cross-section series means some of the probability as the scalar of the Earth matrix, and the luminosity is means how many times the experiments are done in the collider experiments and the detection. So the multiplication of the cross-section and the luminosity gives the event light. So the in the second part, we saw that the experiment pointed out the particle physics, how the particles are produced and how particles are detected.